So we've been examining the effects of feedback on our circuitry, and what we're going to look at right now is the effects of feedback on the impedance of a circuit. So let's look at an example of our series shunt feedback. And as we recall with series shunt, this is a voltage amplifier. Alright, so our series shunt amplifier, the forward amplifier, if we just look at a model of it, would look something like this. We'd have some input resistance that we'll call Rn of the amplifier, or RIA. We have a voltage dependent voltage source that represents our voltage gain. This is equal to AV times VE. And then we have some output resistance, ROA, output resistance just of the amplifier. So this is our forward circuit. Okay, we also have our beta circuit. In our beta circuit, we just have a voltage dependent voltage source that's equal to beta times V out. Alright, so here's our beta circuit. Now we connect this in shunt at the output, so here we'll make our shunt connection. With our output voltage. And in series at the input, so we'll make our series connection here. So we would put our test voltage source across the input of this amplifier, and we'd note that the arrow voltage, VE, is taken across the input resistance, and the feedback voltage, V beta, is taken across the beta circuit. Of course, this is our circuit Vx, and we're going to measure the current Ix that flows out from it. So first thing we note is that Zx, or Zi, is equal to Vx over Ix. And we note that Vx is equal to the sum of the arrow voltage and the feedback voltage, VE plus V beta. We also note that V beta is equal to beta times V out. Alright, now we further note that V out is simply equal to AV times VE. Alright, so now we can express the voltage in terms of just the arrow voltage. Alright, now this term looks like 1 plus our loop gain. Remember, our loop gain is equal to little a times beta, and that's exactly what this term looks like at this point. Now we note that the current Ix flowing through this resistor is equal to VE, so we can also say that Ix is equal to VE divided by R1 or RIA, and we can make a substitution here for Vx in terms of VE and solve this whole equation, and we would find that Vx over Ix is equal to RIA times 1 plus AV times beta. In other words, the series connection increased the impedance of the amplifier by itself by 1 plus the loop gain. So the impedance of the amplifier by itself was simply RIA, now it's equal to RIA times 1 plus T, the loop gain. And so this is better for our amplifier to have this higher input impedance. And what we'll find is that any series connection at the input or output increases the impedance by a factor of 1 plus the loop gain. All right, next we'll look at what happens with a shunt connection.